Hello and welcome everyone. My name is Peter Robinson and today I have got Luca and Roberto who are going to tell us about Ethereum 3-slot finality. So before we kick off, Luca and Roberto, maybe Luca, do you want to go first? Do you want to introduce yourselves?
Yes, hi Peter. Thank you for having me here. Yes, I'm Luca Zanolini. I'm a research scientist at the Ethereum Foundation. I graduated in University of Bern, where I got my PhD in computer science. I worked with Christian Kashan on consensus protocols mainly and distributed trust assumptions for blockchains. And after that, I joined the Ethereum Foundation, and right now my focus is on the theoretical improvement of Ethereum consensus protocol. Specifically, right now, I'm focused on the faster finality protocol, which we're going to present now.
Awesome. And Roberto?
Yeah, hi, Roberto. Thank you again, Peter, for having us here. I'm also work for the Ethereum Foundation. I'm a researcher there, working with Luca on the topic of consensus protocols applied to the Ethereum protocol. I joined and got into the blockchain world in 2017 and 2018. I joined Consensus, where I was there for 6 years. Overall, my research focus has been on distributed system, especially consensus protocols, but also formal verification. Now, at the Ethereum Foundation, I hope I'll be able to get these two things together so we can deliver a better protocol, and also one that has, improved trust guarantees.
Sounds very good. All right. Well, Luca, why don't you share the slides and let's kick off.
Yes. Okay. So hi, everyone. Thank you again for the invite. Today, Roberto and I will be presenting our latest research towards a faster finality protocol for Ethereum, which is called 3SF in this case. We chose to split this presentation in two parts. The first part, which I will present, will be focused on a general overview on how the currently implemented consensus protocol of Ethereum works. So all the terminology, how it works precisely, and also the motivation why it works the way it works. So why it's structured that way and what properties we want to achieve. And Roberto, in the second part, will start from there and builds upon the currently implemented consensus protocol, and will present a faster proposal to make it faster in finalization. So let me first start with some background notions so that we are all aligned with the terminology and everything for the second part. I will actually start from something at the very beginning so that we can build from there so that we can make this presentation as much as self-contained as possible. And of course, the first notion is the notion of consensus. Basically, what we want to build here and what we are dealing with is a system that must agree on an ongoing sequence of blocks or transactions batched in blocks, defining this notion of a chain. So we want to solve this problem of consensus given a set of n parties that must agree on this total order of incoming transaction. And we want two properties to be satisfied all the time. One is safety, which ensures that chains across different honest parties at any time remain consistent, and liveness, that every valid transaction eventually is added to the chain of every honest party. Of course, then we can have also some nuances in the safety property, in the sense that one can have probabilistic safety guarantees or deterministic safety guarantees, but let's not go too much into details. Let's just focus on the fact that what we are trying to build here is a protocol that guarantees these two properties so that everything is consistent and safe and reliable. Over the years, of course, several consensus protocols have emerged, even long before blockchain came to existence, with the differences there were mainly related to the challenges that we had to cope before blockchain, in the sense that before blockchain, as you might know, we were mainly focused on devising consensus protocol for distributed system, meaning systems where we had n parties or n replicas spread across a network. And there the challenge was how to devise consensus protocol that were able to reach a decision in some sense, assuming certain sort of failures, for example, crash failures or arbitrary failures like Byzantine behaviors. So basically there we were able to devise protocols that ensured safety and liveness, assuming that a certain amount of replicas could only crash, or could behave arbitrarily, and that's it. So the goal was, in some sense, to replicate a state in this distributed setting and ensuring consistency. After blockchain, of course, additional challenges came and brought, particularly from the notion of this decentralization of permissionlessness, right? Where now, instead of having sets of n parties centrally controlled, we might have, for example, in the case of Bitcoin, which was the first blockchain that came, a set of unknown parties. So in some sense, the problem there was, how can we solve consensus in a system where we don't know how many people are participating? So new consensus protocol were devised, like, for example, proof of work or this Nakamoto consensus, where given a chain at a specific height of a chain, parties all the time try to solve this computationally hard puzzle in order to be able to gain writing right into the system, and are able to create a block, propose the block, broadcast the block, and receive incentives. Over the time, additional consensus protocol have been devised, also given by the fact that proof of work might not be the final solution in that sense, because there were some discussion about how environmentally friendly proof of work can be, all of this kind of dynamics and discussions. So new consensus protocol came to be developed. And one case is the case of proof of stake. Here, we don't have anymore this notion of having to solve computationally hard puzzle in order to gain rights into the network. But here, parties wanting to be part of the consensus protocol, they just need to put money in stake in order to participate into the protocol. And writing access into the system is granted using, for example, a sort of a lottery where participants are elected proportional to the number of coins that they own, or randomly from the set of validators. Moreover, this proof of stake also enable additional interesting properties, like, for example, accountability, meaning that if some inconsistency are found, then we could potentially identify a set of participants and we can punish them for having misbehaved. So in some sense, proof of stake, although arguably more complicated to devise in order to achieve similar properties of the properties that are granted by proof of work, still enables additional interesting properties. From here on, throughout the course of this presentation, we will be assuming proof of stake. So every time we mention like a party or a validator does that, a validator's votes, a validator proposes, we are assuming that these validators are those entities that put money in stake, and because of that can also be subject to slashing. Okay, in fact, Ethereum moved from proof of work to proof of stake at end 2022, and now is happily proof of stake. So let's see how the currently implemented consensus protocol of Ethereum works. This is called Gasper. As I already mentioned, this is a proof of stake consensus protocol. We have n known validators. So in some sense here, we are kind of going back to the traditional way of solving consensus, because we have n globally known entities agreed. The only difference, one of the differences, of course, is that this validator set can grow or shrink over time. Because of course, if I want to be a validator, I put money in stake and I become part of this set. So everyone will agree that this set will grow. And similarly, if I don't want to be a validator anymore, I just withdraw my money and I stop being a validator. So this set can shrink. For the purpose of discussion here, I'm assuming just that we have n validators, but of course, again, keep in mind that this set can grow or shrink over time. So far, I mentioned the consensus protocol of Ethereum, but under a careful analysis, the protocol of Ethereum can be seen actually as comprising two subprotocols, so two submodules that work in an intertwined way, each one with its own properties and each one with its own reason to be there, which will become clear soon. One of these protocols is called LMD Ghost. This is a synchronous consensus protocol that determines the canonical chain. Basically, it's the protocol that is outputting block after block after block and builds the chain. Here with synchronous, we mean that this protocol, in order to achieve safety and liveness, it needs to be synchronous, meaning that we must assume that there is a message delay bound. There is a message delay bound between messages exchanged by honest validators. So if I'm an honest validator and I gossip something, we assume that within a certain delta, this message will be received by all the other honest validators, which in the case of Ethereum, this delta is roughly 4 seconds. And the second protocol is called Gasper, FFG. This is a partially synchronous protocol that finalizes or irrevocably commits the chain outputted by LMD Ghost. So basically, as a mental model, you could imagine like this LMD Ghost protocol that outputs blocks at specific times because it's assumed to be synchronous. And then we have a protocol that slowly finalizes a prefix of it. Here it's important, this notion of finalization, because the notion of finalization implies some sort of asynchrony resilience in the context of safety. Because as I mentioned before, if some network partition or asynchronous period happens in the system, then LMD Ghost cannot ensure anymore consistency and safety in the blocks that it produces. So we need to rely on the finalized prefix, because we know that whatever gets finalized, it will remain safe even in the face of asynchrony. So in some sense, we have these kind of two modules that work in an intertwined way to provide different properties. So as I mentioned, we have this set of validators. Okay, let's see how more in details how these two protocols work together. We have the set of validators, and they participate in these two consensus protocols at the same time. What happens is that these two protocols work at different timescales. LMD Ghost works with a timescale called slot, which a slot is the time unit in which a block is proposed and voted. Okay, and in Ethereum, this corresponds to 12 seconds time. A collection of 32 slots defines an epoch, and the epoch is the timescale upon which Gasper operates. So we have two different timescales, and protocols work at different timescales. Basically, what happens is that given an epoch, we have the set of validators. This set of validators is partitioned at every epoch in 32 disjoint committees, basically one committee per slot. If we focus on the specific slot, which again is the time unit in which a block is proposed and voted, what happens is that we have a committee associated to this slot, and at the beginning of this slot, a proposer is randomly selected from this committee, and what it does, it creates a block and it appends a block on top of the chain that it deems as valid. What here I mean with valid will become clear in the next slide, but let's say that there is a mechanism in which a proposer, a validator in general, can find the valid chain, and the proposer will just append a block on top of this valid chain, and it will gossip this block around. All the other validators in this committee for this slot will cast a vote, will vote for a block, and optimistically, under good network condition and assuming honest proposer, they will just vote for the block that has just been proposed. So basically what happens here is that we have every 12 seconds, a block proposed, votes on it, block proposed, block votes on it, etc., 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 every 12 seconds. What happens is that we end up building this chain, which is the chain that initially I said, this canonical chain, this chain that is outputted by LMD Ghost. And basically we keep building this chain 12 seconds after 12 seconds. Of course, here in this presentation, I will mainly focus on good network conditions. So I will not tackle like, for example, corner cases, etc. I'm just assuming that we have a good network condition. We have synchrony, we have honest proposers, so that we can actually understand how the protocol should work. And so again, we end up building this chain. And what I mentioned before, that we must have a way to identify the valid chain. And this way is actually made possible through the notion of fork choice function. A fork choice function is a deterministic function that takes all the messages received up until a certain point in time, and it outputs a chain. Now, there can be different ways of defining what a valid chain is. For example, in the case of Bitcoin, the valid chain is the chain that has accumulated the most amount of work over time. And in the context of Ethereum specifically, the valid chain is the heaviest chain that we are able to identify, where the heaviness is with respect to the stake. Because if you remember, every block that is created is also voted. Okay, so whenever a validator votes for a block, it votes with a sort of weight given by the money that that validator has in stake. So basically, what we end up with a chain that over time grows in terms of heaviness given by the votes of these validators. So, for example, in the case of this image, B9, like the chain with head block B9 is the valid chain, and the proposer will just append a block on top of B9. And similarly, this mechanism is also done by the voters. So the voters, before casting a vote, they evaluate the fork choice function. This fork choice function should ideally give the block that has just been proposed, and they will just vote on it. So that's the way in which everything works. So up until now, I was not very specific on purpose, in the sense that, if you remember before, I said that we have two protocols, and given an epoch, a validator gets to talk only once per epoch. And whenever it's time for this validator to talk, it needs to contribute at the same time to both the protocols. So whenever it's, for example, if I'm a validator and I need to cast a vote, this vote must contribute both to LMD Ghost, which is how I just explained, but also to Gasper FFG. This means that validators in Gasper participate at the same time in the two subprotocols. Okay, this means that the voting structure in Ethereum is sort of complicated beast. It's called attestation, and it actually comprises multiple components. So it's not just a vote for a block, but it's a structure and with different elements, and each element is doing something specific. For example, we have the component of this attestation called head block, which is the part that I've just explained, which is the component that is towards the block that has just been proposed in a specific slot. But however, we also have a component for Gasper. The difference here is how these votes are processed, because if you remember, we are working under two different timescales. One timescale is the slot, which is the timescale for LMD Ghost, and another timescale is the epoch, which is the timescale for Gasper. This means that under good network conditions and epipath and all of these good things, votes, so contribution for LMD Ghost are processed slot after slot. Instead, contributions for Gasper are processed epoch after epoch. This means, in some sense, that contributions for LMD Ghost should be different slot after slot, because they are pointing towards the block that is proposed in that slot. However, the contribution for Gasper, in order to be meaningful in some sense, they should be the same across the whole epoch, so that at the end of the epoch, we can process all of these contributions and do something. Okay, so specifically, the contribution for Gasper are themselves divided in two parts. One is called a source, and the other is called target checkpoints. Here, checkpoint is just a technical term. Let's just think of it as a block at a specific high of the chain, which usually corresponds to the beginning of an epoch. So technically, these checkpoints are the first lot proposed in an epoch or the latest block proposed in the previous epoch if no block is proposed in this epoch. And basically what happens is the following. Let's assume that we have an epoch, okay? As I mentioned before, an epoch is made of 32 slots. So across all of these slots, we have new blocks that are proposed and voted on. So the head block component of these blocks will be different slot after slot, and they are processed slot after slot. However, the target, for example, let's consider one epoch. The target for that epoch will be the first block, will always be the first block proposed in that epoch. This means that if at the end of the epoch, when it's time to process this contribution for Gasper, we are able to collect more than 2/3 of the votes targeting or pointing to the same target checkpoint, then this checkpoint becomes justified. Okay, we move to the subsequent epoch, and this latest justified checkpoint, okay, becomes the source for the components of this attestation. And if by the end of the second epoch, we are able to obtain more than 2/3 of votes pointing to the same source, then this source becomes finalized. So as you can see here, what happens is that we need two epochs, two consequent epochs to finalize a block. And again, as you can see, we process contributions in different ways. So the contribution for Gasper here are processed epoch at the end of an epoch, so while moving to the next epoch. And instead, contribution for LMD Ghost are processed slot after slot. So this, in some sense, is the way in which Gasper works. Okay, so we are building a chain with LMD Ghost, which is a very fast way of building the chain, and slowly we finalize a prefix of it. And the way in which we finalize is through this mechanism of source target, source target, source target at every epoch. So of course, some of you might wonder, why do we need two protocols? Cannot we just have just one protocol that does everything? The answer actually is no, and there is a reason behind that. The reason why the consensus protocol works the way it works, the way I just presented, is in some sense rooted in the philosophy in which Ethereum wants to provide guarantees in the chain, in the sense that ideally what we want is to provide kind of the same guarantees that the Bitcoin protocol provides. Specifically, we want to keep building a chain, even if we have new parties like joining or going offline, coming back online. So in some sense, we want this notion of dynamic participation or dynamic availability. To be more precise, if we want to go more academic here, we want to model a distributed system in which participants can be either online or offline, meaning that their participation is dynamic. So what we want is to be able to keep building a chain, even if 99% of the validators go offline, okay, while maintaining the guarantees of safety and liveness. This actually, so this doesn't really necessarily happen in Ethereum, because of course Ethereum has a sort of incentives and penalties for validators to be offline and to be online and to not be offline, meaning that if you are online and you are timely casting votes and you're participating correctly to the protocol, you get incentives. And if you are offline for too long, you might end up being penalized. However, what we want to prevent is, for example, crash failures in the context of client teams. For example, in May 2023, a bug affected two implementation of the consensus clients of Ethereum protocol, Prism and Teku, and roughly 60% of participants went offline for like 25 minutes. The chain, of course, halted finality, because for finality, if you remember, we need more than 2/3 of validators to be online and voting and vote. However, the chain kept growing due to LMD Ghost. Turns out that we cannot have one protocol that meets all the following requirements. There is an impossibility result that says we cannot have a consensus protocol meaning that guarantees safety and liveness, according to what I presented at the very beginning of this presentation, and that can allow for this dynamic participation in the validator set, and that can tolerate network partitions or asynchronous periods, meaning that if we want to have a consensus protocol that guarantees safety and liveness, so a secure consensus protocol that can tolerate participation to fluctuate over time, this protocol must be synchronous, and which is exactly the assumption that we have for LMD Ghost. So this LMD Ghost is this dynamically available consensus protocol that keeps outputting a chain even if participation is varying, or even if there are crashes in some clients. So over the years, new ways of overcoming this impossibility result have been devised. For example, this is the case of this even flow family of protocols by Noitas and Se, which in some sense correspond to the way in which the protocol of Ethereum works, right? Because we have what they propose is these kind of protocols that are themselves divided in two subprotocols. One that takes care of dynamic availability and that keeps outputting a chain, assuming participation can fluctuate. And in the case of Ethereum, this is taken care of by LMD Ghost. And on top of it, a partially synchronous component that finalizes a prefix of it, which is exactly what Gasper FFG does. So the Gasper protocol kind of works this way. And the reason why it works this way is because we want to achieve this dynamic availability, but at the same time, we also want to preserve part of the chain in case network partitions happen, because of course, assuming a network being all forever asynchronous in this context, it might not be a good assumption, unless of course you increase the delta of by much. So what we want is, in case of good network conditioning, in case of good synchrony and happy path, etc., we have this LMD Ghost that keeps outputting chain 12 seconds after 12 seconds, even if 99% of the validators are offline. If we have also full participation, that we have finalized prefix that is taken care of by Gasper. And even if we have network partition or asynchronous periods, then this finalized prefix doesn't change. And the problem here is that now back to very soon to Roberto, is that, as you might have seen, it takes a while to finalize, in the sense that it takes optimistically 2 epochs to finalize, meaning roughly 15 minutes. This means that the chain is constantly falling behind, in some sense, quote unquote, of 15 minutes of blocks, even assuming good network condition, even more, of course, if we don't have full participation or we even bad network conditions. This means that we might have this unfinalized suffix that might get reorged if asynchrony or something happens. So the goal here is we want to keep these guarantees that I just described, but we also want to be able to finalize faster, in a faster way. And this is exactly what our proposal is doing. So we have this 3-slot finality that now Roberto will present. And to conclude, we also want an additional property. And this additional property is called reorg resilience, which is we want to guarantee that honest proposals made under synchrony will remain always canonical, meaning that we don't want that an honest proposer proposes something under synchrony might get reorged, which is actually something that currently could happen for LMD Ghost. So here, our work was driven by 2 reasons. One reason was to make the protocol faster in the finalization, and another reason was to make the protocol safer, because over the years, some attacks have been shown targeting LMD Ghost. So what we wanted was to first devise a secure and safe dynamically available component, and then to combine with Gasper in order to achieve a faster finality. And so, yes, now back to Roberto.
Thank you, Luca. I think you need to unshare so I can share.
Yes, okay, of course.
Great. I hope you can see the slides. So thank you, Luca, for setting the stage, we thought that we need to discuss 3SF, which is our proposal for a faster finality protocol and real resilient protocol for Ethereum. I'll start the presentation of 3SF by focusing on the dynamically available protocol. As you can see from here, we considered in our work potentially two different kinds of dynamically available protocols. One is, let's say, based on the heaviest chain concept, which is very similar to the LMD, to the current LMD protocol that is used by Gasper. And the other one is a quorum-based dynamically available protocol. Now, quorum here does not mean 2/3 of the validators. It's a dynamic quorum because, as Luca said, we are in a setting where some validators might crash, might go asleep. So the quorum must adjust based on the perceived level of participation. But regardless of which dynamic available protocol we use, either of them have the same structure in terms of slot. So the slot is divided in 4 parts. Each part lasts delta, where delta is a known constant, which represents the maximum time under stable network condition that it takes for a message sent by an honest validator to reach all other honest validators. The first phase is the propose phase. As you can imagine, this is the phase where the validator that is selected to be the proposer proposes a block. This is followed by the vote stage. At the vote stage, validators, they vote for a block. If the network is synchronous, you have a good network condition, and the proposer is honest, the honest validators will vote for the block proposed by the honest proposer. If either of these conditions are told, then it really depends on the circumstances. After the voting phase, we have the fast confirmation phase. Now, before explaining what fast confirmation means, I need to explain what confirmation means. In the context of dynamically available protocol, we use the term confirm in a way to express safety. Meaning, we said that we confirm a chain to mean that we ensure that this chain will always be a prefix of the dynamically available chain seen by any honest validator. Of course, under the conditions that the network is synchronous, because it is the condition required by dynamically available protocol, and also the condition that roughly the majority of the validators are honest. What fast confirmation then means? It means that we are able to confirm under the conditions that you see written here, the block proposed in this slot, in the same slot. This is why it's fast. There are situations where we cannot do this, and one of the simplest to explain is the scenario where less than 2/3 of the honest, basically we have online less than 2/3 of the honest of the total validator set. Under these conditions, confirmation can be delayed. So it could be that the block that is proposed in the current slot will be confirmed in some slots in the future. So under certain conditions, we can confirm here the block that is proposed, and this is kind of very important for the overall protocol. This is followed by the freeze stage. The freeze stage, nothing much happens. So what happens is that honest validators take a snapshot of the set of messages that they've received so far. And this freeze stage is used to essentially synchronize the set of messages that the proposer of the next lot uses to propose a block, and the set of messages that the validators will use in the next lot to vote. This synchronization is what essentially gives us this reorg resilience property for the dynamically available protocol that is then extended also to the overall protocol. One thing to note is that in FINSF, we don't have committees compared to Gasper. We assume that we have the entire validator set votes in a slot. Now, this can be, of course, there is a question, can we do this? There are perhaps yes, perhaps no, but there are possible different solutions and trade-off, like using subcommittees. This is in a way a parallel line of research. But in what we present today, we assume that there is no committee and all validators vote in a slot, and the messages can be delivered within the time. Also, we parameterize the vote with an expiry period, meaning that we only consider the most recent votes, and we don't consider all votes. What this expiration period gives us some resilience to short period of asynchrony. So even though like this dynamic available protocol relies on synchrony, by having this expiry period, we can essentially determine, we can cope with short period of asynchrony that lasts less than this expiry period. The question, well, why don't we set this expiry period to infinite, so we are resilient to any asynchronous period? Well, the problem is that if we do that, we go back to a situation that our protocol becomes less dynamically available. We will need always at least half of the validator set to be online. So there is a trade-off between resilience to a synchrony period and the level of dynamically availability. Regardless of the dynamically available protocol that we use, what happens is that the proposed stage, the fork choice function is called, and the fork choice function, Luca mentioned, is this function that outputs one of a chain, which is, as you know, there can be multiple branches. This fork choice function will output a chain. This is used both in the propose and the vote stage. I will explain later a bit how the details of this, but I want just to give you an overview of the differences between RLMD and RLMD fork choice and the MFC fork choice, where MFC if the fork choice used for the quorum-based dynamically available protocol. As you can see from this diagram, if you use RLMD, what it does, it starts from a stable block and progresses down the block tree by selecting it every time the subtree with the highest weight until it reaches a leaf block. So in this case, it reaches block B22. On the contrary, MFC, which stands for majority for choice, it goes down a subtree only if that subtree, only the weight of that subtree is larger than half of the maximal amount of weight that any subtree could ever have. So in this case, because we get to when we get to B21, none of the children has a weight that is larger than 50%, so it stops there. So the difference between the two fork choice functions is that the MFC one doesn't necessarily output a leaf block. Now looking at the going back to how the slot and how the protocol unfolds. If you consider RLMD, this is, as I said, very similar to RLMD, Ghost, and what happens is that at the proposed stage, the proposer will build a block that extends the output of the fork choice function. And at the vote stage, validators will vote for the output of the fork choice function, which, if the proposer is honest and the network is synchronous, will actually be the block that has been proposed. Whereas when we transition to quorum-based, to the quorum-based approach, where the fork choice function is this majority-based fork choice function, again, the proposed stage is similar. The proposer will extend the output of the fork choice function. Whereas in the vote stage, as you remember before, the fork choice function is not guaranteed to output a leaf block. So what's going to happen is that if the block proposed extends at the voting phase, if the block that was proposed extends the output of the fork choice function computed at the voting stage, then honest validators will vote for the block that has been proposed. Otherwise, they will vote for the output of the fork choice function. So under the condition that the proposer is honest and we have synchrony, we have the same property that we had before, that honest validators will vote for the block that has been proposed. Now, what these dynamically available protocols give us, they ensure that honest proposals are not going to be reorganized. It prevents balancing attacks, avoids ex-ante attacks. The chain ensures the chain continues to grow even when we don't have full participation. And also, as I mentioned before, we can be resilient to short period of asynchrony. However, if we just take these dynamically available protocols, we don't have safety under asynchrony, and also we don't have finality. We don't have the concept of finality. To do this, we need to integrate this dynamically available protocol with essentially a finality gadget. Again, as I mentioned beginning when I started talking, this is a proposal for faster finality, which is a 3-slot finality. There is another previous proposal by Luca and Francesco, which was achieving faster finality in one slot, but with some different trade-offs in a way. Anyway, today I'll focus on 3-slot finality. One of the peculiarity of 3-slot finality is that we have only one voting phase per slot, whereas in the other proposal we have multiple voting phase per slot, meaning that the slot was actually longer. With 3-slot finality, the major trade-off is that we get a shorter slot time. So looking at how the structure of the 3-slot finality protocol looks like, you see essentially the same stages as before, as we looked at the dynamically available protocol. What changes is the vote stage. In the vote stage, we don't only cast vote for the dynamically available protocol, but we also cast FFG votes, which we call them FFG for historical reason, for the as they're called in this way with Gasper, and they serve the same purpose of ensuring, providing finality. Where again, FFG votes are those that are take care of providing safety under asynchrony and providing finality. I'm going and okay. Yes. So in the epi path, when we have a synchrony, the epi path is the path where synchrony, honest proposer, full participation. In this case, a proposal block, or the block that is proposed in slot T, is voted by at least 2/3 of the validators and become fast confirmed. So that's where fast confirmation comes into play. Under these conditions, which is what we need anyway to guarantee something is finalized, the block that is proposed will be fast confirmed in the same slot. And then over the next slot, this block will be justified. And in the following slot will be finalized. I will go into the details, more into details later of how this happens. But before doing so, I want to explain a bit how justifications and finalizations work under 3-slot finality. So let's start with this example. Let's look at, we are at slot 0. We just have a block. So let me just actually give you concept of checkpoint. A checkpoint in 3-slot finality is a pair of a block and a slot. So in this case, what we see on the screen is a checkpoint composed of block 0 and slot 0. Now we move, say, to slot 5. We have, say, this chain. And and we have potentially where any of these blocks in this chain can be paired with slot 5 to create a checkpoint. And assume that you have the red arrows represent FFG votes. And we assume that we have just 4 validators. So we see we have 3 FFG votes between the checkpoint B0, 0, 2 targets B2, 5, and 1 target B3, 5. The modified justification rules that we have in 3SF ensure that allows us to justify B25, B15, B05. If we are going to use just the justification rule of Gasper, none of this would be justified because the justification rule of Gasper requires that the source and the target are the same. But in 3SF, we had to weaken this condition to achieve all the properties we wanted to achieve, and actually we allow the target to be different. What we require for a checkpoint to be justified is essentially surrounded by a majority of FFG votes. Like if you take B15, it's surrounded by 3 votes that start with B0, which is an ancestor of B1, and target B2, which is a descendant of B1. Now, if we move to slot 7, we have, for example, a longer chain. Again, here we can pair any of these blocks with slot 7 to create a checkpoint. Assume we have this condition with these additional FFG votes. These additional FFG votes will justify, using the same rules as before, checkpoints B47, B37, B27. Again, like if we take an example, B27 is surrounded by 3 FFG votes, starting from an ancestor, which is either B1 and B2, and targeting a descendant, which is either B4 and B5. When I say ancestor, a block is ancestor of itself and also descendant of itself. Now, if we go to the slot after, slot 8, assume that we have this condition where we have a bunch of FFG votes, all with the same source, a potentially different target, but with the slot of, but with they span only in one slot, meaning that the slot of the source is just one lower the slot of the target. This is what gives us finalization. So because of, which is similar to what we have in Gasper. So because of these FFG votes, we are going to finalize the chain B3, from B3 to B0. Again, if you are in Gasper, this wouldn't be the case because Gasper requires source and target to be the same, but we weaken this condition and we allow the targets to potentially be different. As long as the only requirement essentially is the same source and the slot of the target must be one higher than the target, the slot of the source. Now that I've given you a brief idea of how justification and finalization work, I go into details of how a block gets finalized. Suppose we are in this scenario, the proposer of slot 5 proposes block B4, which is a descendant of the chain B3, B2, B1, B0, and assume that the honest proposer at the beginning of slot 5 sees B13, the checkpoint B13, as the greatest justified checkpoint. What's going to happen is that, first of all, because of the this view merging property that is inherited from RLMD, from the dynamically available protocol, we are able to sync the view of what the greatest justified checkpoint is between the proposer and the validators at the voting time. So the voting time, all of this validator will see B13 also as the greatest justified checkpoint. And because of this, they will send FFG votes with source B13. Now the target of the FFG votes is the block they see as confirmed. Remember, confirmed means in assuming the condition of synchrony, a confirmed block is a block that will always be in the chain output by any honest validator. But this can be different. This can be different, but it's not a problem for us. And so if you just consider the red votes, we will see that we have this justified checkpoint with slot 5 would be B1-5 and B2-5. Again, because they're surrounded by 3 votes with starting from an ascendant and target a descendant. But however, we can have the Byzantine nodes, and the purple vote is represents the vote by a Byzantine validator. And if some validators receive this purple vote, then B3-5 is also justified, because again, same rule. We have 3 votes targeting B3-5, so B3-5 is justified. So is B2-5. What this means is that when you progress to the next slot, you see what you have here is that the FAG votes, that is the second set of FAG votes, they might have different sources, because the source that used by an honest validator is the greatest justified checkpoint that they see. But as I said before, this potentially can be different because of this existence of Byzantine vote. However, in slot 6, so the next slot, because of the fast confirmation protocol, the block that was proposed in slot 5 before is going to be fast confirmed in slot 5, and that will be used as target by honest validator in slot 6. So as you can see, no matter what, they might have different sources, but the target will be B4-6. The target will be the block that was proposed by the honest proposer. Then we move, and as a consequence of this, we justify B4-6 and B3-6. What matters is that B4-6 will be seen as the greatest justified checkpoint by any honest validator at the next stage. And because of this, you see the last set of FAG votes, they have all source, they all have the source, the checkpoint B4-6, and potentially different target, but this doesn't matter. As by following the finalization rule that I explained before, as consequence of these votes, because B4-6 was justified, and now we have FAG votes with source slot 6 and target slot 7, so just span one slot. This leads to finalizing B4. One thing I want to note, to point out, is that we made no assumption on whether the proposer of slot 6 or 7 are honest, dishonest, propose anything. It doesn't matter, as long as our assumptions for this say happy path to happen is that the proposer of slot 5 is honest, and we have synchrony, which if you consider partial synchrony, you have passed GST, and also that we have at least 2/3. Say we have. If you look at the set of validators that are online, we have the number of honest validators is at least 2/3 the total number of validators. I'm going to conclude by speaking about slashing. Now, as explained, we weaken the conditions for justification and finalization. As you see, this requires a tightening, in a way, an additional condition on slashing to prevent Byzantine nodes from finalizing conflicting block without being slashed. As we have in Gasper, we have a 2 slashing condition. One is a double vote, where you send 2 different votes with the same target slot, but for different blocks. And the other one is called surround vote, where basically, if you just look at the slots of the votes, the source slot and the target slot, you have 2 votes and they surround each other. So like the one, as you can see here, we have the source of the second vote is, in terms of slot, it becomes before the source of the vote at the top, and then the target slot of the vote at the top is lower than the target slot of the vote at the bottom. Now, if you look at this vote, this couple of votes. This in Gasper is not slashable. This is because both votes have the same, the source of both votes is the same slot A. And before we require that for slashing to happen, we require, made a mess. Wanted to go back. Okay, before we were requiring that A was less than B. In this case, A is equal to A. So in Gasper, this wouldn't trigger a slashing. But this is not a problem because in Gasper, because for justification, we require that FFG votes have the same source and target. This situation can never happen that you justify 2 checkpoints with the same slot but different blocks. It can never happen unless at least 1/3 of the stake is slashed. But this can happen in 3SF because you can justify more than 1 checkpoint for a given slot. So in 3SF, we need to add this additional condition, and actually, the actual condition for slashing is not that before is an ancestor of B5, but we slash as long as in this example, the slot in which before was proposed is before the slot where B5 was proposed. So that we need in terms of slashing is adding this condition. Concluding, with this finality gadget, we are able to achieve the 2 properties that the dynamic available protocol were not giving us, meaning that, namely, that the protocol provides safety, even if asynchrony doesn't hold, and also the protocol provides faster finality. And this concludes the presentation. Thank you all.
You shouldn't be thanking us. We're thanking you.
You need to show the slides at the end?
No. I was just saying it's yeah. We thank you for doing both of you for doing a great talk. Okay, are there any questions? Obviously, very clear. Yeah. So there's a few questions that I have. So one is, so it feels like the signature aggregation or the signing is something that is an open piece of research. And I remember when I was part of consensus research, there was some sort of signature aggregation scheme where you had, like where you were able to combine many signatures together incrementally, essentially log 2. Is that a sort of scheme that's been thought of, or have you just assumed that someone will work it out and not put time into working out how the signature aggregation works?
Can start with this. So I think the protocol you're referring to is Endol. As far as the code, like one of the problems in Endol was that it requires validators to know the IP address of the other validators, and like there is a debate on whether, well, there is some debate because actually the P2P protocol can be de-anonymized anyway, but the time like there is, in a way, like, it's not a black and white thing, and there is some concern about the fact that you need to know exactly the IP address. Generally speaking, this is a problem that we need to sort out. There are, the easiest solution is just to say that, you consider the validator set to be, say, 10,000 validators, and remove and ordered by stake. So those that have lower stake and they don't fit in, they are not part of the validator set. Now this can be potentially problematic, of course, for solo stakers. However, with Petra, there'll be an EIP rolled out that enables consolidation of stakes. So big stakers can consolidate multiple validators into one, which will reduce anyway the number of validators, and which will help a lot. And also potentially one argument there is that small validators, they can organize themselves using some sort of decentralized staking pool to be able anyway to be part of the validator set. Or there are different type of research, which is again about containing the validator set. This research is called Orbit, which constrains the validator set, but at least gives you the property that the rewards are proportional to your stake, regardless of even though if it's a small stake, you might not always be part of the validator set. However, your rewards will be proportional to the stake that you have. Or there are also, potentially research on how to perhaps improve the networking in order to be able actually to aggregate more signatures than what we can do today. But this is also like tied to another stream of research, which is about having post-quantum secure signature aggregation protocol, which makes the entire thing more challenging.
Yes, I think, yeah, definitely. Okay, Stefano asked, how does three-slot finality fit with Orbit's proposal, brackets advantages and risks, and what's the risk of having an economically weaker committee attesting for finality?
So, do you want to go, Luca? No.
Yeah, I can just start. Wanted to mention that Orbit, in some sense, and all of this mechanism for handle the validator set is a sort of side research, in the sense that 3SF is a generic consensus protocol that works assuming this, what Roberto mentioned, that in every slot we don't have epochs anymore, we have only slots, and in every slot the whole validator set votes. Of course, then here with the whole validator set, quote unquote, is something that can be handled and can be obtained through different mechanisms. One mechanism is, for example, Orbit, SSF. Other mechanisms are, I don't know, like having different sort of committees or other signature aggregation schemes. But in some sense here, with Orbit, the goal would be to kind of preserve a sort of economic finality guarantees that we have in the context of the whole having now that we have now. With the goal there is basically we select a committee based on probability, kind of like, for example, we could potentially set a threshold, and we say all the validators that have more than this threshold will always be part of this core, this orbit, this kind of core set of validators, and then on top around it we can have validators where proportionate to their amount of stake can be part of this set with some likelihood, like, for example, some fraction or something. So the goal is, in some sense, to preserve the sort of economic finality guarantees that we have now. But as Roberto said, of course, like solo staker, there are a lot of advantages, but also there are a lot of discussions about how to cope with people that have very, very little stake. I don't know if, Roberto, you want to add something.
Not necessarily, not what you said. I was just going to try to address a bit the question by Stefano. Yeah, that's one of the trade-off. Like if you have the Orbit committee, you have a weaker economic security. So like that's part of the design space and the constraint. So yeah, that is a problem of Orbit.
Okay. Well, thank you. Yeah. So Mark asked, with the Australian election coming up, for those people who don't live in Australia, in about, I don't know, 2 or 3 weeks, we've got an election, federal election. Anyway, with the Australian election coming up, I started to think during the talk about whether preferential voting could help, but probably not because you probably don't know other candidates when you're voting. So in Australia, everyone has to vote and you get fined if you don't vote. And you vote for your preferred candidate and in order your other candidates that you would prefer, like, so from say 1 to 10 or something. And that's how we do it in Australia. So it's, and in some localities, we've got optional preferential. So you can just vote for the first candidate and not vote for the rest. But yeah, typically, I think at federal level, it's preferential and you must vote for the lot. So could you do preferential voting? So say this block, but if people don't like that block, I like that block as well. Would that help, or is that just going to add more data?
Interesting. Not sure. Like as Mark was saying, though, like what is your second preference? I don't know. It's
Maybe one.
So you're saying
Oh, sorry, go
yeah,
ahead.
sorry. But I might not. So here with preference, you mean like because the first preference I can imagine is the block that has just been proposed, right? And the second preference, yeah, right now I cannot.
Yeah. What about if there was a block that had been proposed and not enough people voted for it, and then another block got essentially proposed as an alternate to that? So people said, look, that block is invalid. I'm not voting for that. And, so you've got a fork happening, and maybe you've got like a three-way fork. Could you end up, saying, I like that one and I like that one, but I don't like that one?
Well,
sure.
indirectly is what is happening, I think, already. Like, not, of course, by choice, but for example, if we use the quorum-based for choice function, in some sense, we indirectly are saying we prefer the block that has the majority of support on it. If you're using RLMD Ghost, people are saying we are preferring the block that is heavier, that is heavier than the other. So it seems that indirectly we kind of are already doing this. I don't know. Maybe if I'm just very stretching the reasoning here, but yeah.
Yeah. Maybe take it on as something to
Yeah,
think about,
yeah.
as a possibility. Have you done any performance?
The Australian for choice.
Yeah, Australia. Yeah. Yeah. Have you done any performance analysis? Because I'm looking at this and thinking about the range of information that could be coming at a node. And if you had, say, 10,000 different pieces of it, like from different 10,000 different nodes, and they've all got different pieces of information that you've got to assimilate to work out what's actually been agreed on. Is that super computationally expensive, or what does that look like?
Yeah, I mean, your question is pretty spot on what we are working on at the moment. As you noticed, it's quite like computing these justification finalizations can be computationally quite heavy. So the moment we are working on variation of this theoretical algorithm we are presenting today in order to have something that is more efficient. We have not run any test at the moment,
Yeah.
At the moment, we just want to get to a point where we are able to compute justification and finalization, and it's done today in the actual Beacon chain implementation, where you associate a state to a block. And when you receive a child with the state associated to the parent and the child, you are able to compute the next justified, the greatest justified and greatest finalized. Because the algorithm that we presented today is really recursive. So in a way, you need to have used the entire set of messages you received so far, which is not doable. So that's what we are working on at the moment.
Yeah, okay. Yeah, I can imagine trying to come up with a maybe slightly not as good but more efficient protocol would be something that because I was just looking at it and just thinking about it and thinking, would feels like a supercomputer needed for each node, but I don't know. All right.
But other ways, because like if you remember, like in the epi path, it's always true that either all the votes have the same source, or they all the same target. So even though like we consider when there's find justification, even the possibility where all targets are different or sources are different, that's actually not true in the epi case. So that already allows us to simplify things a lot.
Yeah, but you've got to assume worst case, because I mean, otherwise someone will attack the system, fire up 5,000 validators and specifically try and break consensus.
Oh, no, you can just, because like what you want to show is that this doesn't break safety, but you want that, it makes sense to guarantee that finality is achieved only when you have synchrony and the proposer is by an honest validator. So like if, for example, if you have a situation where you don't have, like, you can just discard votes that are, like if you have a bunch of votes that have the same source and you have another one that some isolated that have a different source, you can just discard them. You can just not consider them.
Okay.
This would be...
Oh, sorry. Are there any other questions? Yeah, okay. Oh, yes. So what are the next steps? Where are you going to from here?
The next step is what we're working on now, trying to come up with an implementable algorithm. After we have achieved that, we'll be writing a specification of this protocol. It's likely that this more efficient algorithm will require some sort of trade-offs. So producing a document, explaining the trade-offs and why we chose those trade-offs. After this specification stage, what I envision, there will be definitely a proof of concept stage where some small set of team we start implementing it and testing it out. I hope in parallel with that, we can also apply formal verification to the protocol to ensure that this optimized version is still correct. As usual, optimized version are harder to analyze, so that will be, but two things can progress in parallel.
Okay. Yeah. 4-slot finality won't have quite as good ring as 3-slot finality.
Yeah, actually, it's with a trick to the protocol, it's possible also to achieve the 2-slot finality. But it becomes slightly more complex, but has the same properties.
Okay. Interesting. Could you reshare this? Did you get those last slides included in your...
Yeah. Okay.
Could you show them, please?
I need to make a modification that you, Peter, noticed, like these blocks 65, 66, 67.
Yeah.
This is the small typo.
If you do that, I won't get around to sharing the talk until on YouTube until tomorrow. So if you do it before then, that'll be awesome.
Yes.
Okay.
Yeah, of course.
The merch store is open, so feel free to buy a t-shirt. Next slide. And so we've actually got 4 talks lined up. So next, in 2 weeks' time, we've got a very deep dive on the Bybit hack and other related hacks by our friendly expert. We've also got a talk which is on the intersection of blockchain and AI, which will be really interesting. The 28th, I should have updated this, but I didn't get to it. That talk is actually going to be on Succinct and how they've been able to allow people to very simply create a ZK rollup and using the OP stack. And then on June 11th, there's something called EOF, which is essentially like a new EVM, which is coming to Ethereum. And essentially it's EVM v2. I think you could almost think of it as. And by June 11th, I'm going to know a heck of a lot about it and be able to do a great talk. But at the moment, I'm, it's one of these things. It's coming out in Vukasa hard fork, probably, which is going to be towards the end of the year. Or maybe it might slip to 26, but I think originally it was aiming for September this year. So anyway, something very important to know about. Next slide, please. All right, if you're here today, you can catch this talk on YouTube and the link to the slides. If you're watching it on YouTube, you want to come along and ask tricky questions live, then please join the meetup and RSVP for talks. There is a Slack workspace, please join it. Sometimes there is example code, certainly for the EOF talk, there will be example code and it'll be in that repo. So look, Luca, Roberto, thank you very much for showing or telling us all about your research and, where things are up to. It's, it's looking like maybe not tomorrow, but, maybe in 2026, there'll be a hard fork coming to us and we'll suddenly have 3-slot finality, which would be absolutely awesome.
Great. I like your optimism, Peter.
Yeah, I know complicated changes take a long time to come through, but yeah, it can all happen in time, and I think there are great possibilities.
Cool. Thank you for having us.
Not a problem.
Thank you very much.
Yeah, thank you. All right, talk to you later, everyone. Bye-bye.
Bye. Bye.
Okay. Bye-bye. Thank you.